This is NeSLAM. NeSLAM focuses on the combined integration of neural radiance fields and visual SLAM technologies. Throughout this project, we aim to develop a more accurate and custom NeRF algorithm while designing a general pipeline to benchmark the best method of obtaining quality NeRF renders. Multiple industries are experimenting with NeRF and VSLAM and are projected to implement both. These fields include emergency responders, mechatronics, healthcare, and more. For example, emergency responders have been using VSLAM to localize mobile robots and could gain more information by integrating NeRF onto their systems. This project will refer to the following. For implicit scene representations, they encode the spatial location, geometry, and appearance of objects into a memory-efficient and compact form by using neural networks. One example is NeRF, which represents objects and scenes used in view synthesis, something very similar to 3D reconstruction. On the other hand, we have discrete scene representations, which update scenes through direct observations and is not memory efficient. We obtained ColMap data by using a RGBD camera and running ColMap. ColMap then outputted a file containing the camera's intrinsic calibration matrix and each image's transformation matrix. This file could then be passed into NeRF Studio. We obtained OrbSLAM data by recording data and running OrbSLAM. However, the output file contains camera positions in quaternion. Using the equation above, we converted the quaternion into a transformation matrix for each image. Then, the entire text file could be converted into a NeRF Studio compatible file. We tried to obtain keypoint images for each data image to pass into NeRF Studio in a similar manner. We also used the NeRF Studio library to easily access different NeRF algorithms, with each algorithm having its own specific input requirements and using a different neural network feature. We tested our data against many other algorithms as possible in order to document the pros and cons of each. When creating our custom NeRF algorithm, NeSLAM, we drew inspiration from a possible trend across multiple NeRF and VSLAM integrated algorithms. That an increased use of local MLPs resulted in improved output renders and better algorithm performance. Thus, we developed our code to use 3 MLPs to identify coarse, medium, and fine scene details, instead of just coarse and fine details as used by MIP-NeRF. We also used NeRF to store data efficiently rather than hierarchical feature grids as used by NeSLAM.
We initially recorded 3 sets of data, all of which was processed by ColMap successfully. However, the longest video could not be further processed by NeRFactor due to an overwhelming amount of images and keyframes to match. As mentioned before, OrbSLAM did not have many supported library features for custom data. As such, we experienced issues while obtaining the output data as it required changing code and adding custom modules. For example, while we were receiving images keyframe coordinates, we weren't able to extract keyframe image. We could not show the image itself in NeRF Studio's visualizer. We spent a lot of time making OrbSLAM compatible with the rest of our pipeline as our research indicated OrbSLAM could provide faster and more accurate camera poses. Moreover, we tried many NeRF algorithms, but some could not run properly due to incompatible input requirements and technical issues. For instance, MIP-NeRF could not work as it required Blender data, which is a data constructed in Blender application before outputted in specific format. We could not convert our custom data into Blender as the Blender data is usually synthetic instead of the real-world data. We also ran instant NGP, but after 57 hours, the model did not progress and stopped working, shown in the table. Moreover, we tested vanilla NeRF, but it could not run as the input data was also incompatible despite different attempts to alter the code. Similarly, NeSLAM could not run despite changing several parameters such as the data managers and parsers. Nevertheless, our original hypothesis of ranking NeRF Studio algorithms was correct for the data we could test, as NeRFactor outputted data much faster than instant NGP. All in all, we learned that NeRF and VSLAM integration will be useful in the future as NeRF can be used to save detailed scenes in a memory-efficient manner. After adding VSLAM, user can save scenes as a mechatronic system traversed throughout possibly dangerous environments. We also learned RPNs may optimize future NeRF renders pipelines, as shown by NeRFactor outperforming instant NGP. Finally, we believe our project was most restricted by our computer power, as we only have one computer capable of running NeRF Studio. Nevertheless, we have learned a lot, and thank you for watching.